All right, so we're going to look at heats of reaction. And in this, you're going to look at how much heat is produced, how much energy is produced or absorbed in a chemical reaction. And then you're going to use that to determine kind of if you burned this much methane, how much energy would you get? All right, so what we know so far. We know that chemical equations can give off heat or absorb heat, exothermic or endothermic. Change in heat can be represented in chemical equations in delta H notation and on energy graphs. Delta H is always the same for a balanced equation. Q is the quantity of heat in an entire system. Okay. Now, I'm going to tell you something. I never ever teach this formula. I'm going to cross it right out. This formula is stupid. You don't need to know this formula. It's moronic. I leave it in the books for some odd reason, but I never teach it because there's a better way. We're going to use the fact that these things are ratios. All right, so we got a lot of examples to work for. Here's the type of question that we have down here. All right, so we've got this chemical reaction for burning methane, right? Now what this means is we've got 1 mole of methane plus 2 moles of oxygen will give us 2 moles of water and 1 mole of carbon dioxide. And then we're going to get 802.3 kilojoules of energy out. All right, so the question is, how many kilojoules of energy are released when 123 grams of methane burns? So we're going to burn this much methane. The question is, how much energy are we going to get? Okay, so we're going to skip over this stuff because it's stupid as well. We're going to get right down to this on the next page. I'll show you how we solve this using simple ratios. No delta H, no Q, none of that. Just ratios. Okay, so we're going to write up this chemical reaction up here. Again, 1 CH4 plus 2 O2 gives us 2 H2Os plus 1 CO2. And we get a total of 802.3 kilojoules. Now, here's what we know. We are going to burn 123 grams of CH4. Okay? Now we know that burning 1 mole of CH4 will produce 802.3 kilojoules of energy. Okay, so now what we want to do is we kind of want to take this out of the equation and put it in delta H form. So delta H is equal to negative 802.3 kilojoules. Like that. Okay, so if we burn 1 mole of CH4, we're going to get that many kilojoules of energy out. That means if we burn 2 moles of CH4, we're going to get double that. If we burn 3 moles, we're going to get triple that. If we burn 4 moles, we're going to get quadruple that. So we just need to figure out how many moles of CH4 this is. 123 grams is how many moles of CH4. So the first thing that we're going to do is we're going to find the molar mass of CH4. This is something that you've done before. All right, so we find the molar mass. So we're going to do this in a few different color pens. We're going to find the molar mass of CH4 from the periodic table, right? C is 12.011. H is 1.008 times that by 4, figure out the total, and way up my calculator, it's over here. We figure out the total here. I don't know where the heck my calculator is on this. I mean, I should be able to do this in my head. I do these enough. 12.011 plus 1.008 times 4 equals 16.043 grams per 1 mole. Okay, so this is 16.043 grams per 1 mole, and mole is MOL is the short form. So if 1 mole has 16 grams, how many moles are there in? 123 grams. If there's 16 grams in 1 mole, how many moles are in 123 grams? So step 1, I figure out the molar mass. Step 2, I have to figure out how many moles of CH4 I'm burning. So to do that, okay, so I'm going to draw a map here. I know my grams of CH4. From my grams of CH4, I can figure out my moles of CH4. Right, to do that, we use our 16.043 grams per mole conversion. So I know my grams, and I'm trying to figure out my moles. My grams is 123 grams. Okay, so this is my map. I have 123 grams. Now I have to figure out how many moles there are. Well, since I don't know moles, I write it like this. How many moles are in 123 grams of CH4 if 1 mole of CH4 has 16.043 grams? And I read it like that in my head every time. So then I just do my multiplication here. I take 123, I multiply it by 1, and then I divide it by 16. Simple. 123 times 1 equals 123 divided by 16.043. 7.7 moles. So my question mark is 7.7 moles. So 123 grams of CH4 is 7.7 moles of CH4. Now I goes from my moles of CH4 to the energy, to my delta H. And I do that by using my periodic table. 1 mole of CH4 gives me that much energy. So because I know my moles and I don't know my energy, I put my energy on top. So when I read it like this, again, the reading, it's important. I say, how many kilojoules of energy do I get from 7.7 moles of CH4 if I get negative 802.3 kilojoules of energy for every 1 mole of CH4? Then I cross multiply. 7.7 times that divided by that. It's just going to be 7.7 times 802.3. Now, in my calculator, I don't have 7.7. I actually have 7.66689529191. And I leave that in the full decimal form in my calculator. I just multiply by 802. Oh boy, I messed that up. 802.3 equals 6,151 kilojoules of energy. There's my answer. And it's negative, right? Because it's an exothermic reaction. We're losing that amount. So what I did was I start with what I knew about CH4. I knew the grams of CH4. Then I went from the grams of CH4 to the number of moles of CH4. And then I used my equation up here to figure out the energy of CH4. Hopefully that makes sense. When we do the next example, it'll probably make a little more sense. All right. The next example uses the same equation, this equation up here. How many kilojoules of energy are released when 45.5 liters of oxygen are consumed in the burning of methane, where 1 mole of O2 is equal to 22.4 liters of O2, STP, standard temperature pressure, from the ideal gas law? So in this one, I'm going to build a map again. What do I know? I know my liters of O2, right? That's right here. That's how many liters of O2 I've got. Then from my liters of O2, then I can go to my moles of O2 using this conversion right here. 1 mole is 22.4. Then from my moles, how many moles of O2 I have, then I can go to my energy, my change in H. By using this conversion, 2 moles of O2 will give me negative 802.3 kilojoules of energy. So, let's start with this. First thing, I'm going to write down what I know. I know that I've got 45.5 liters of O2. And I'm trying to figure out my moles. So to do that, I put my moles on top. I say, how many moles will there be in 45.5 liters of O2 if 1 mole of O2 is 22.4 liters? So how many moles of oxygen? Remember, mole is just a count. How many moles of oxygen are there in 45.5 liters of oxygen if 1 mole of oxygen is 22.4 liters? Now, you remember what moles are, right? I hope you do. If you don't, please come ask me and we'll work it out. So I do this on my calculator. I do my cross multiplying. 45.5 times 1 divided by 22.4. which ends up being 45.5 divided by 22.4. So my question mark is 2.0 moles. The actual answer is 2.03125. Okay, now, so I keep that in my calculator. Now I write down 45.5 liters of O2 is 2.03125 moles. Now I have to go from moles to energy. Well, I don't know my energy, do I? So I write, but I do have a conversion from up here. This is my conversion rate right here. 2 moles of oxygen burned will produce 802.3 kilojoules of energy. So there's my conversion right there. So to do this, I write up how many kilojoules of energy am I going to get for 2.03125 moles if I get 802.3 kilojoules of energy for every 2 moles O2. Right? That's just from up here. 2 moles of O2 gives me 802.3 kilojoules. I just cross multiply this times this divided by that. So do times 802.3 equals divided by 2 equals 814.8 kilojoules. So if I burn 45.5 liters of oxygen in this chemical reaction, I will get 814.8 kilojoules of energy out. All right, so we're going to work with this procedure in more examples, and then you'll do questions on it.